Very good morning to all of you. So last time we have defined condition number for a given matrix A where it is pre-assumed that A is an invertible matrix. Moreover, the norm is here is any of the subordinate matrix norm. Okay, right. And what we have obtained is if you perturb the vector B to obtain a new vector B tilde, then the solution X is also be perturbed by X tilde, and both will satisfy the following relations: AX equals to B and AX tilde equals to B tilde. Then we were interested to find how X and X tilde differ in relative terms, and we found the following inequality for the same. So note that if you call X is exact solution, X is an exact solution of the system of AX equals to B, okay, and X tilde is an approximate solution, okay, then you will, if you perform AX tilde, you are going to get a vector B, the B tilde, a new vector B tilde, and that you wish to see how much B tilde is close to the vector B. Okay, so now we define new terms here. Okay, so we define some of the new terms. The one of the term is notation E, which is defined as X minus X tilde. So difference of exact solution and approximate solution. So it is called an error. Okay, error vector, because X is a vector, so E is also a vector. And we define an R by B minus AX tilde. So that we will be observing because we wish to see how AX tilde means B tilde is closer to B. Okay, so if you write clearly, okay, if you write a little carefully, what is R here is, what is R is B minus AX tilde. That is nothing but B is what? AX minus AX tilde. So that is equals to A times X minus X tilde. That is equals to A times E. Right? Okay. And this will also gives you, okay, this gives you, okay, R gives you what? Okay, R gives you how much close, okay, how R gives you how much B and B tilde differ. Okay, the closeness between B and B tilde. Okay, right? So moreover, so just now we have defined the relation R and E are related by equation, by relation R equals to, or AE is equals to R, right? Okay, so we will be able to get, once you know the R, you will be able to get E by performing basic Gauss elimination method. Okay, if it is not applicable, then you can go for Gauss elimination with pivoting strategies. Okay, instead of, we are not going to seek Okay, the solution like E is equals to A inverse R, though we are assuming that A is invertible matrix because to make it computationally effective and with less cost. Okay, because inverse of the matrix will cost you more, computationally very expensive. Okay, for large order matrix. Okay, so instead of this, so we are not going to follow the inverse here. We are going to solve the above by for getting E by the following with basic Gauss elimination method or Gauss elimination method with pivoting strategies. Make sure that the sufficient conditions for the existence of or for applicability of Gauss elimination methods with or without pivoting strategies. So this R is called, so E is called error vector. Okay, E is called error vector and R is called the residual vector. And they are related with the bound. Okay, they are related with the bound. Okay, they are related with the bound that 1 by k of A norm of R by norm of B is less than equals to norm of E by norm of X less than equals to k of A time norm of R divided by norm of B. Okay, so if condition number is large, then that error term will be large. Okay, so little perturbation may affect if the A is so sensitive. You can say the matrix A is so sensitive that little perturbation, okay, the condition number is large, okay, for with respect to a subordinate matrix norm. Okay, infinity norm you can use or one norm you can use or any other subordinate matrix norm which you may comfortable. More preferably you can go for two norm as well. Okay, and see what can you do when the system is well conditioned. So we will be saying, so we will say a system is, okay, a system AX equals to B, okay, is ill conditioned if the k of A, the condition number is large. So this word is very important here, large. So how much large it is, that also depends. So what we can say, if it is of moderate size, then it is acceptable. Okay, so what is required is, like suppose you are, so a system AX equals to B is well conditioned. Okay, A is called well conditioned if k of A is of moderate size, means in acceptable mode. Okay, means it's not so large. Okay, however it may large, but it may not more large. Okay, right. Okay, so that you decide based on the bounds, how much close residual vector is and so on. Okay, right. So let's consider an example here. So what is the example here is, using the infinity matrix norm, compute the condition number of the following matrix. So it's clearly depends on epsilon. Okay, so here epsilon is any greater than 0 number. Okay, so for this matrix you can find A inverse. So if you find the determinant of the matrix, determinant of this matrix A is equals to epsilon square, that you can verify. It's very easy, you know, 2 by 2 matrix, how to find a determinant of it. So this is 1 by epsilon square time 1 1 minus 1 minus epsilon, okay, and minus 1 plus epsilon, right? Right, okay. So what is the norm A infinity? Is maximum over row sum, right? Magnitude sense. So 1 plus 1 plus epsilon, that is 2 plus epsilon, first row sum in magnitude sense. For the second row you have magnitude of 1 minus epsilon plus 1. So epsilon is greater than 0, but we don't know how much far it is. Okay, so we can assume here is, so here is 1 plus magnitude of 1 minus epsilon. So if epsilon is greater than 1, okay, if epsilon is less than 1, it is 2 minus epsilon, because 1 minus epsilon is positive in that case. So you can talk with different cases. So you can assume here, one more assumption you can make, that epsilon is, so we are assuming, okay, I'm assuming that, assume that for simplicity epsilon is less than 1. Okay, so this is 2 minus epsilon and that is 2 plus epsilon, so that is 2 plus epsilon, norm A infinity. What about norm of A inverse infinity norm? That is equals to, yeah, okay, maximum of 1 by epsilon square plus 1 plus epsilon by epsilon square, comma 1 by epsilon square plus 1 minus epsilon by epsilon square. Since epsilon is less than 1, so 1 minus epsilon remain positive, so magnitude is also the same. Okay, so what it will be, maximum of this is equals to 2 plus epsilon by epsilon square. Okay, so if I wish to write the condition number, so the above two, this implies the condition number with respect of A with respect to the infinity matrix norm, that is equal to norm A infinity times norm A inverse infinity, that is equals to 2 plus epsilon times 2 plus epsilon by epsilon square, that is equals to 2 plus epsilon by epsilon whole square. So we have assumed that, so now it clearly depends on epsilon. So let epsilon is less than equals to 0.01, right? So this implies, what does this implies is, this implies epsilon, so if from here this is epsilon is less than equals to 1 by 100, this implies 1 by epsilon is greater than equals to 100, okay, right? So this implies 1 by epsilon square is greater than equals to 10,000, okay. Moreover, what is 2 plus epsilon is, so this implies 2 plus epsilon by epsilon is greater than equals to 2 plus epsilon times 100, right? So that is equals to 20100 divided by 100, right? Wait a minute, right? Epsilon is less than equals to 0.01, okay. So right? Okay, so from here what you can tell is, so this implies 2 plus epsilon by epsilon whole square is greater than equals to 2 plus epsilon whole square times 100. And okay, and what you can tell is yeah, epsilon is less than equals to epsilon 0.01. So this implies 2 plus epsilon certainly greater than equals to 2. So this is near about 0, right? Epsilon is near about 0, so certainly greater than equals to 2, right? So this implies 2 plus epsilon by epsilon square is greater than equals to 4 by epsilon square, which is greater than equals to 4 times 100 square, so that is 10,000, so that is equals to 40,000. Right, so k infinity of a, so the condition number for epsilon less than equals to 0.01 is huge, more than 40,000. Okay, so this matrix system, corresponding matrix system will be ill conditioned, so it is not moderate size, it cannot be said is of moderate size. Okay, so you need to be careful while choosing the matrix, choosing the for saying the matrix that the given system is ill conditioned or well conditioned. So at the start, at the first stage itself, you should discard the system if it is of ill condition. Okay, if it is of well condition, then you will proceed for, you can say, iterative methods and so on. Okay, right. So this is what we have discussed just now. Okay, right. In the last class we have also shown that the condition number is at least 1 for any invertible matrix. For any invertible matrix we have condition number is at least greater than equals to 1. The second result is actually shows that for what type of matrices, the condition number is 1. Okay, and with respect to which norm. So that is very that we have also seen that if G is an orthogonal matrix, okay, then if you look at the 2 norm, okay, if you recall, when you say orthogonal matrix means G transpose Z is equals to I, and G inverse is its transpose. Okay, so both will share. So what this will imply straightforward, spectral radius of G transpose of G is also 1. And you know that 2 norm of G is nothing but the square root of spectral radius of Z transpose Z, that is 1, square root of 1 is 1. So that also result has been shown. And moreover, for Frobenius method, so for Frobenius norm, the condition number is achieved 1, n, okay, for an identity matrix. Okay, right. And the last result also has been discussed just now, that a matrix with the last condition number is said to be ill conditioned. Okay, with the last condition number. So that is, if it is of moderate size, that system is acceptable and we will be proceeding to solve, okay, for the same, right? Okay, right. So now our next topic is to derive Neumann series and iterative refinement. So before going further now, so let's see how this definition of norms are useful for on our system of linear equations Ax equals to b. Okay, so now let's recall. We say let V be a vector space. Let V be a vector space. Okay, let V be a vector space. Okay, and let this defines norm on V. Norm on V. For example, you can take V as Rn. Okay, so for an example, okay, so for an example, V is equals to Rn, and you can take any 2 norm, 3 norm, okay, P norm, infinity norm, and so on. Okay, so then we say, okay, then we say this pair V comma this norm is a non-linear space, is a non-linear space. You can also show that, okay, that n cross n, okay, that also I have left as an exercise, okay, that n cross n, okay, which is set of all matrices of order n cross n of order n cross n with respect to the following operation. With respect to following operations, okay, so A plus B, so there are 2 matrices of order n, they are means like Aij n cross n plus Bij n cross n, is that vector addition is Aij plus Bij, and the scalar multiplication alpha A is defined as alpha time Aij n cross n is defined as replace every element by multiply by alpha. Okay, becomes a vector space over R. So we are talking about over the field R only, and the matrices with at current stage with real entries. Okay, so this will become a matrix space, and the corresponding norms you have defined, that subordinate matrix norm or Frobenius norm. So along with any norm, this will becomes a non-linear space. Okay, now what our aim is, okay, what our aim is to define notion of convergence in V comma norm. So as previously stated, this norm is a generalization of modulus function, okay, in a rough manner. Okay, so you have seen that, okay, on R, if you look at on R, we say that a sequence xn converges to X if there exists a natural number capital K such that mod of xn minus x is less than epsilon if for every epsilon bigger than 0, there exists k belongs to natural number such that mod xn minus x is strictly less than epsilon for all n greater than equals to k. Right? So how it will look in multi-dimensional space. So this R is a one-dimensional space, right? So how would you define? So, or in other words, you can say this in other words, limit n tends to infinity mod of xn minus x is equals to 0. Okay, right? So for defining notion of convergence in V, a nonlinear space V, so we assume that V is already associated with an norm. Okay, right? So let Vk be a sequence of vector in V. Okay, we say that Vk converges to a vector in V in V if following happens. Okay, if limit n tends to infinity norm of Vk minus V is equals to 0. Okay, so now this norm is, let us denote with suffix V. Okay, because it is associated with V. Okay, so let us denote it with suffix V. Okay, now note that this norm is very important. When it is going to be important when you have V is an infinite dimensional spaces. Okay, so so here we wish to make remark. Okay, we wish to make remark. Okay, we wish to make remark here. Any two norms on finite dimensional non-linear space V are equivalent. So if I wish to say, when you will say two norms are equivalent, so definition is, so we say that this norm, let's say this is 1, this is different from the norm 1, so let's instead of this, let's say this is norm and this is norm star with star. Okay, are equivalent on V if there exists alpha comma beta in R. Okay, so V is a vector space over a field R we are talking about. If there exists alpha beta belongs to R such that, okay, alpha time norm is less than equals to norm star less than equals to beta time norm. Okay, so whether you say norm is equivalent to norm star or norm star is equivalent to norm, both are the same thing. Okay, so this is the definition to say two norms are equivalent. So what we have just now made remark that on a finite dimensional vector space or non-linear space, any two norms you take, they are equivalent. So that is well established result in linear algebra. So you must have seen that, okay, or otherwise you can refer the book by Gilbert Stein. Okay, so or you can ask me in comments, or you can ask me through email. Okay, so I will refer you the notes for the same. Okay, so how does it help us that two norms are equivalent on infinite dimensional on finite dimensional space? So if you, so you note that, okay, not that, okay, not that, not that. So m n cross n is a, and with any norm is a non-linear space and it's a finite dimensional. So whether you work with subordinate matrix norm or Frobenius norm or any other norm you define, okay, they all become equivalent. And if you talk about the convergence of the sequence in the matrices set, okay, mn cross n, or you can say mn cross 1 column vectors, okay, they all are, this is also n cross 1. What is this? This is the, okay, let me this, not that, this is a finite dimensional, and you have Rn comma any norm. So they are finite dimensional vector spaces. Okay, are finite dimensional normed linear spaces. Okay, normed linear spaces. Right? So you start with any sequence of vectors and you work with respect to any norm. Okay, which one is you may feel comfortable or which may be easy to approach to show that that corresponding sequence is convergent with respect to the given norm, okay, or with respect to the considered norm, then it will automatically will imply that it will converge with respect to any other norm on the Rn or on mn cross n. Okay, so that is going to be useful when you are going to generate the sequence of approximate solution and repeatedly by using the iterative methods, and what you wish to achieve is the desired solution. Okay, so whether it is going to near to the solution or not, that can be told by with respect to any norm. Okay, right, okay, so this is what, and moreover if I look at here, this is almost the same thing here. If you look at here, okay, if you look at here, so this is almost the same thing to say, like the sequence of vectors in V given by Vk is getting closer to V here as k tends to infinity. As k tends to infinity, as k goes to large, then it is getting closer to V, or distance between the vector Vk minus V is tending to 0 as you go for large k. Okay, so you can look it for any practical example here. Okay, so I will just refer the example. Okay, let's have, okay, V is equals to, let's say R3, okay, and let's define a sequence Vk by the vector, let's say this is minus 3 plus k inverse, this is minus 2 by k inverse, 2 by k, and last is e to the power minus k. Okay, so if you look at here, so what will be, so if you from the intuitions, what you can see that the limit, what it will be, limit must be as k tends to infinity, 1 by k tends to 0 and e to the power minus k tends to 0. So k is here is k is tending to infinity, k is greater than 1, okay, greater than 1, non-zero number, okay. So this tends to minus 3, 0, 0. This vector should tends to this vector. Okay, so you can talk about any infinity norm here. Okay, right? So you can see, so infinity norm, if you look at here, so what is norm of Vk minus V infinity? Maximum over the magnitude. So if you look at this, so magnitude of minus 3 plus k inverse minus 3, so 1 by k, comma minus 2 by k, so that is 2 by k, comma e to the power minus k. Okay, so that is going to be maximum over this side, and this is certainly, you can show that the maximum tends to 0 as k tends to infinity. So certainly it is going to be e to the power, and I think this is going to be e to the power minus k is strictly less than 1. Okay, so it is going to be equals to 2 by k, right? Okay, right, this maximum is, so e to the power minus k, okay, goes to goes to 0 exponentially, right? Okay. Okay, so now similarly you can also define the Cauchy criterion on vector spaces, on finite dimensional vector space. Okay, now if V is an infinite dimensional, whether the things remains true or not, that you can understand by an following example. Okay, so let's take an example of an infinite dimensional space. Let's say V is a vector space and a set of all continuous function on the closed interval 0, 1. Okay, so let V equals to set of all, you can say set of all real valued, I am talking about real valued continuous functions on closed 0, 1. Okay, so this is a vector space with respect to the addition of two functions and scalar multiple of a function. Okay, that is so that is f plus g of x is defined by f of x plus g of x, and with respect to what is the scalar multiplication, alpha f of x is alpha time f of x for all x belongs to 0, 1. So with respect to these two operations, this becomes a vector space, and it is an infinite dimensional vector space. Okay, and now there are two norms. So one norm is defined by, let's say, norm x. Okay, norm x is defined by, let's say, this is a infinity norm, that is a maximum of mod of xt, where 0 less than equals to t less than equals to 1. So this is exists, right? This norm exists. Why? Because x is a continuous function on a closed interval. Okay, so hence uniformly continuous, and it implies that it attains its maximum and minimum both. Okay, the second norm what I am going to define here is, that is integral norm. So that is defined as integration 0 to 1 mod of x of t dt. So this you can show that they actually define the norm. Okay, now we are going to look the behavior of the sequence in this vector space. Okay, so this also can be verified because x is a continuous function, so composition of two continuous function is continuous, because x is composite with magnitude function, so magnitude of and this function is continuous, and hence continuous function is integrable, right, or Riemann integrable, right? Okay, so these both norms are well defined. Now we wish to, let's take sequence. Okay, let you take x of, let x of t is equals to, or x and t is equals to, define as t to the power n 0 less than equals to t less than equals to 1. Then if you look at, then you can show that norm of xn infinity norm, okay, that is must be 1, that is equals to 1, because maximum, this is increasing function, t to the power n is belongs to natural number. Okay, n belongs to natural number, so t to the power n is an increasing function, so it attains its maximum at the right end point of the interval, so that is 1, t equals to 1. So that is, then norm x and infinity is 1. On the other side, if you look at norm of x and 1, okay, that is equals to what? Integration 0 to t 0 to 1 t to the power n mod, because it's always positive, so this is dt, that is equals to t to the power n plus 1 by n plus 1, the upper limit minus lower limit, so that is equals to 1 by n plus 1. So this tends to 1 only, you take as n goes to infinity. On the other side, this tends to 0 as n tends to infinity. Okay, so with respect to this integral norm, this converges to xn converges to 0. Okay, but with respect to infinity norm, this the same thing is not happening. Okay, right. So in the infinite dimensional space, the situation becomes complicated, and it is not as easy as in finite dimensional vector spaces or non-linear spaces, right? Okay, right. Okay, so what now we are going to show is, now we are in the position for establishing a result. Okay, in, you can say, in a theorem, let a be a matrix of order n. Okay, if norm of a is less than 1 for any subordinate matrix norm, then I minus a is invertible. Okay, then I minus a is invertible. Okay, moreover its inverse is given by I minus a inverse is given by the following infinite series: k is equals to 0 to infinity a to the power k. Okay, so this series is called Neumann series. Okay, so this series is called Neumann series. Neumann series, which actually converges to the inverse of the matrix without computing its inverse. Okay, so how it is going to be useful, that we are going to see by an example. So let's first see this result, that if norm a is less than 1 for any subordinate matrix norm, then I minus a is invertible. So here, if you try to see the proof of this as follows. Okay, so let us assume that let I minus a is not invertible. Not invertible means it's a singular matrix, right? So this implies there exists a non-zero x in Rn such that I minus a x is equals to 0. Okay, this system will have a non-trivial solution. Okay, I hope you agree with this. Now if you rewrite this is nothing but x equals to ax. Now this implies norm of x is equals to norm of ax. Since this is a subordinate matrix norm, this is less than equals to norm a times norm x. Now it is given that norm is strictly less than 1. So this is going to be strictly less than norm x, which is not possible because x is a non-zero vector. So norm x is a non-zero number. Okay, so which is not possible. Which is not possible. So which assumption made this is I minus a is not invertible. So hence our assumption is wrong. So this implies I minus a is invertible. So it's a very simple proof here. In a minus a is invertible. Now let's prove or let's get that series convergence. Okay, so now we wish to show that next we wish to show that that I minus a inverse is equals to summation k is equals to 0 to infinity a to the power k. Okay, right. Now means this is what this is equals to, if I write this is limit n tends to infinity summation k equals to 0 to n a to the power k. So this is the limit of the partial sum of this. Okay, so if I show that, okay, so what I will show is I will show that I minus a time summation k equals to 0 to n a k is converges to I. If I show this, then I am through. Okay, if you multiply both sides by I minus a, since this is a constant matrix without depending on k or n, okay, so it can be taken inside, and if I show that this is equals to I, then I am through. Okay, so right. So now to show this, what now if I look at carefully the following partial sum, this is summation k equals to 0 to n a to the power k, that is equals to summation k equals to 0 to n a k minus summation k equals to 0 to n a to the power k plus 1. And if you expand all the things, okay, what you will get is this is equals to minus a to the power k plus 1, and I think I minus a to the power k plus 1, right? This is going to be this. Now this implies I minus a, so I am just writing here summation k equals to 0 to n a to the power k is equals to I minus a to the power k plus 1. Now this implies I minus a time summation k equals to 0 to n ak minus I. I'm just subtracting I on both sides and taking the norm, subordinate matrix norm, okay, on both sides, and using the fact that I'm using the for the subordinate matrix norm, this is submultiplicative, that's less than equals to norm A into norm B. Okay, so if I use this fact, this is less than equals to norm A to the power k plus 1. If I keep on applying this, now since norm A is strictly less than 1, this tends to 0 as k tends to infinity. So I'm through. So this implies, okay, this implies I minus A times summation k equals to 0 to n. A to the power k is tends to I, the identity matrix. Okay, hence our result, hence our claim that, okay, hence this implies I minus A inverse is equals to summation k equals to 0 to infinity A to the power k. Right? Okay. So let us so for explaining this, we are going to consider the following example from the Kincaid book. So in this example, we are supposed to find the inverse of the following matrix. Okay, so I wish to find the inverse of the following matrix. But if you go back and look at the Neumann series, okay, what it is giving you? The inverse of I minus A. Okay, right. So for the same, so what I am going to write is, now for finding the solution, so let B is equals to I minus A. Okay, so let B is equals to I minus A. So we wish to see that whether it is invertible or not. So means we wish to first find what is A. So this implies A is equals to I minus B. What is I is? I is an identity matrix. So if you take the difference, so what will be? This implies A is equals to, okay, 1. 0.9, this is 0.1, okay, 1 minus, right, 0.2, 0.3, 0.2, 0.3, I minus B, that is right, minus 0.1, minus 0.1, 0, 0.1, 0.3, minus 0.3, minus 0.2, and minus 0.1. Right? So if you look at carefully, so you are supposed to see that whether norm of A is less than 1 or not with respect to any subordinate matrix norm. So I am going to look for infinity norm. Okay, so whether this is true or not. So what is the infinity norm? Is maximum over row sum. Okay, so maximum over row sum in magnitude sense. So norm of A infinity, if you try to find out maximum over row sum, so row sum in magnitude, so 0.1, 0.2, 0.3 is 0.6. So first row sum in magnitude is 0.6, second row sum is 0.2, third row sum is 0.3 plus 0.2 plus 0.1, that is 0.6. So maximum is 0.6, which is certainly less than 1. So the result shows that this implies I minus A is invertible. I minus A is invertible. Means B is invertible. So means this implies B is invertible. Okay, B is also invertible. Now from the Neumann series, so This implies B inverse is equals to summation k equals to 0 to infinity a to the power k. Okay, right. So, but in computer you can't go for infinite sum. So you should go for up to some 20 or 19 power. So it is rather easy or rather computationally less cost. Okay, it bear less cost than finding the inverse. So if you recall, the first step is for k equals to, you can say k equals to, so which is summation k equals to 0 to capital N a to the power k. So n is how large is, how much large is, as large as possible. So for n equals to 0, so if I take for n equals to 0, what is B inverse is a to the power 0, that is nothing but the identity matrix. So that is how we will define by the convention that the matrix power 0 is identity matrix. For n equals to 1, you have B inverse is equals to I plus A. Okay, so that is equals to I plus A. Okay, so if I make I and plus A here is 1.1, right? 1.1, 0.2, 0.3, 0.3 minus 0.1, 1, 0.1, right? Minus 0.3, minus 0.2, and 1 minus 0.1, that is 0.9. Right? Now similarly for n equals to 2, you have B inverse is equals to I plus A square. So every time you are adding, okay, so here you can perform the loop. So in I you are adding, next step is adding A, then you are adding in the new step A square, in the new step you are adding A cube, and so on. Okay, right. So in this way you can go for, okay, till n large possible. So you can go till n equals to 18 or 19, and you can match with the exact answer as well. Okay, right. Right. Okay. So next we are going to in the next session we are going to look for how the iterative methods will take place. Okay, and we will see when we will say they are convergent. Okay, right. Thank you.